Missing a magic pen. That's trouble. Hello, Internet. We're about to do infinite series if we can find a magic pen. It appears to be missing. I bet it's in Pete Hermberg's pocket. You guys see anything? And the other one's not working at all. Well, it's not good. All right, let me go steal one from the room. See if this works. All right, so infinite series. So consider one of my favorite numbers ever, 1/3. A lot of people like decimals better than fractions, and so if we take 3 into 1, we find that we get this decimal that goes on forever, that we can approximate at any point in time. If I read this out properly, then what I have is 3/10 and 3/100 and 3/1000 and going on forever. Okay, so I have the sum of a sequence. Anytime you have a sum of a sequence, you have a series. Often I'll use the word series, meaning infinite series, but series aren't necessarily infinite. I could stop at any point here. If you stop somewhere, you get what's called a partial sum. So if I have an infinite series, a partial sum means I didn't go all the way. So for example, if I wrote S with a subscript of 3, that means what's the third partial sum of this, which means add up the first 3 terms, which is exactly what I have written above without the dots. So 3/10 plus 3/100 plus 3/1000. If I'm going to do more than a few terms, then it's nice to have a formula for it so I can abbreviate it with summation notation. So I'd like to find a pattern to the sequence here. Well, let's think about that for a second. So any particular term is going to have a 3 times some power of 10. Then the question is, can we name the power of 10? Well, this is the first term, that's the second term, that's the third term. 1 0, 2 zeros, 3 zeros. It looks like the power of 10 I want is the nth power of 10. Does that seem reasonable here? So 3 over 10 to the n is my nth term. Sometimes we have to use multiple letters because with a partial sum, usually n is the stopping point, not the variable I'm summing over. So for example, if I wanted to say, well, what's the nth partial sum look like here? Then I would make a summation up to n, which means my variable for the summation has to be something else. And I is usually a popular one. I think our author likes k. I prefer I, not to be confused with the imaginary number. And so my partial sums would be 3 times 1 over 10 to the I. Sometimes sums will start with 0 Sometimes they'll start with 1, sometimes 2. Although when we're doing sequences, we usually say there's a first term, a second term, and a third term. With sums, sometimes it's more convenient to start with 0. Sometimes it's more convenient to start with 2. Just kind of depends on the formula that we have. So for example, I could rewrite this sucker right here and say S sub n is equal to the sum as I goes from 0. And then in this case, if I start at 0, I don't need to go up all the way up to n, because that would give me n plus 1. So I'm going to go to n minus 1. So going from 1 to 10, for example, there's 10 numbers there. Going from 0 to 9, there's 10 numbers there, right? And then I would have 3 times 1 over 10 to what power? Well, let's see. I want to have a 10 to the first, then a 10 to the second, then a 10 to the third, but I'm starting at 0. So I think this should be an I plus 1 down here. So sums can look slightly different for the same set of numbers, just depending on whether you start your sum at 1, counting at 1, or you start counting at 0. And you just got to always pay attention to that. Where did we start? We start at 0, did we start at 1? And it depends on the problem. Sometimes 1 is more convenient, sometimes 0 is more convenient. Okay, so an infinite series has a limit. So infinite series, yeah. Sure, yeah.
Is everybody comfortable with us doing that? Be the backs of your hands. And it's a remote video, and if you prefer not to be in it, just let me know.
Oh, too bad I don't have my magic whiteboard up. Oh, maybe I'll try to hook that up. Give me a sec. I'm going to give you guys a problem to do.
Are you sure you're comfortable? Okay.
You're okay. All right. So yeah, give me 1 sec. I'll be right back. Consider different problem. Oh, duct tape. It'll be okay for a minute. 0.1111 repeating forever. Can we come up with a limit for that? Yes. You guys think about that for a sec. I'll be right back. All right, let's see if the magic whiteboard will work today. Plug in the magic dongle. Oh, we got a flashing light. That's a good start. It's settled in. It's going to orient. All right. It's our lucky day. We get to be on camera and have the magic whiteboard. Does anybody have any thoughts about that one right there? What number that might be? All right, we'll come back to that in a second. So as far as the series having a limit, we usually call that S. That's always going to be the limit as n gets big of the partial sums. So we have to look at the partial sums and see if there's a pattern. Now, in that other problem, we already know that there's a pattern. We know that 1/3 is equal to a bunch of 3's repeating. And we just established that that sum could be written as I goes from 1. I'm going to let this go to infinity there. When I put an infinity here, it means the limit of the partial sums. 3 times 1 over 10 to the I. Now, I is the variable, right? So the 3 is just a constant. We can pull that constant out of the sum. So what we have is 3 times the sum of 1 over 10 to the I as I goes from 1 to infinity. And so that's just 3 times 1/10 plus 1 100th plus 1 1,000th dot dot dot. Eventually it'll be a 1 over 10 to the n and then it just keeps going. So what we want to do next is prove that it's going to be 1/3. And there's a couple of ways we can do that. I'll do a low-tech version, then a high-tech version of it. The low-tech version is that ... is quite annoying. It goes on forever. If I could get rid of the infinite tail, I'd be doing good. So the low-tech version is, let's say S, our sum, is equal to this. So we're going to make an equation. How many places are repeating? Well, that's based on our base, which is 10. 1 power of 10 is repeating. So what I'm going to do is I'm going to compare this to 10s. What's 10s going to look like? 3 point, blah, blah, blah. And what do both of these have in common? Well, they've got that infinitely long tail. What's a good way to get rid of something like that? How about subtracting it? Okay, so if I subtract these guys, I'm going to write the s underneath. Then that infinitely long tail is going to vanish on us. So on this side, 3/10 subtracts, 300 subtracts, 3,000 subtracts. Forever and ever and ever, those guys disappear. The only thing that's going to stick around is a 3 on that side. On the other side, I have 10 s's minus 1 s, which is going to leave me 9 s's. So wonderfully, that infinitely long tail is now gone. And so I can say, hey, s has to be 3/9. 3/9 is really 1/3, which is what we knew in the first place. But this gives us power we didn't have before, to be able to take something that has an infinite tail and try to get rid of that tail. Okay. So we're going to take a slightly different approach on this by looking at it not as just a simple repeating decimal, but as the sum of a bunch of terms instead. Okay. So let's go with the more interesting version. S is equal to, thanks. Let's do the simple version of S where we just have the 1, forget about the 3, because that's just a common multiple. So we've got 1/10 plus 1/100th plus, eventually we have that 1 over 10 to the n. I'm glad he's gone. Okay, was I going too fast? Oh. Okay, so I'm going to just take that idea that I had before. Now, just for now, now S goes forever, right? S sub n means we have to stop at whatever n is. So S sub n would be 1/10 plus 1/100th plus ... Stop right there, don't continue. There's no plus ... No infinitely long tail. So we're going to just ditch the tail for a second. But what I want to do is say, well, let's see what happens if we multiply this. Now I'm going to change what I'm multiplying by. Before I multiplied by 10, here I'm going to multiply by 1/10. Why 1/10? Because that's the common multiple to get from one term to the next. Okay. So what does 1/10 s sub n look like? Well, it would be 1/100th plus 1/1000th plus all the way up to what? 1 over 10 to the 1/10 times 1 over 10 to the n, 10 to the n plus 1, right? And just like before, I'm going to pull that subtraction trick. So I'm going to say, well, let's just subtract these two rows from each other, minus all of this stuff. And things line up, like these guys volunteer to go. Right next to this, there is a 1 over 1,000. Right before 1 over 10 to the n plus 1 is what? 1 over 10 to the n, so it's going to volunteer to go away with that one right there. So a bunch of stuff collapses when I do that, just like it collapsed in that other version of the problem. So what I get is 1 s sub n take away 1/10 of an s sub n is going to leave me 9/10 of S sub n. And then on the other side, I'm going to get 1/10 minus 1 over 10 to the n plus 1. I lost a whole bunch of stuff in the middle. I collapsed it. And then cleaning this up, I would just multiply by the reciprocal. So S sub n is equal to 10/9 times all of that. Let's see, minus 1 over 10 to the n plus 1. Okay, so let's see. Cleaning this up a little bit, the 10s kind of divide out a little bit. So I'm going to get a 1/9 out front. 10 times 1/10 is 1. 10 times 1 over 10 to the n is a minus 1 over 10 to the n. Sorry, 10 to the n plus 1. So what I was able to do is collapse the partial sum into this little bitty version of it. So what I've discovered is that if I look at the partial sum, which normally says go from 1/10 all the way up to 1 over 10 to the n, no matter what I pick n to be, that's always going to be the same as 1/9 times 1 minus 1 over 10 to the n. So I have a shortcut formula now. So if somebody says, well, I need the 100th partial sum here, I don't need to add up 100 terms. I just go straight to my shortcut there. Cool thing about my shortcut is I can now consider the limit as n goes to infinity of these partial sums, which is what S is, right? Where are these sums headed? So then I have the limit as n increases of 1/9 times 1 minus 1 over 10 to the n. And I can pull the limit into this if the limit of each piece exists. Well, there's no n's here, there's no n's there. So as long as that limit exists, I can pull that limit through. So let's see, as n gets big, 10 to the n is getting very big. 1 over a very big number is pretty close to 0. So what we have from our previous experience with limits is that that part right there is going to 0. So I have 1/9 times 1 minus 0, which is just 1/9. Now, we looked at a similar problem to this the other day. Instead of adding up 1/10ths and 100ths and so on, we added a half to a fourth to an eighth to a 16th. Remember that in class the other day when I was trying to walk 1 meter a little bit at a time? That's a very similar problem to this right here. Okay. All of these types of problems where I have a sequence of powers of something. Does anybody remember the name I gave those kinds of sequences the other day? Starts with a G. Those are geometric sequences. Yeah. Once I start adding up geometric sequences, I get geometric series. And a geometric series is something that looks like, usually they write, let's see, as I goes from, let's see, what do we start with? I think I'll start with 0 up to n of a times r to the I. So that's kind of a standard looking geometric series. What does that look like? Well, if I equals 0, r to the 0 is 1, so the first term here would just be a. Second term, if I is 1, I'll get a times r. Third term would be a times r squared, and so on down the line, all the way up to the last one, a times r to the n. Is this an infinite series or a partial sum? It's a partial sum because I decided to stop at some number called n. Yeah, so this is a partial sum of a geometric series. Yes, unless n equals infinity, but typically we try to let n be a real number, a counting number, which infinity ain't one. Infinity is a direction. It means go that way. Which way? I don't know, that way. whatever that way is. Partial sum of a geometric series here. There's nothing special about having 1/2 as your R, like we did yesterday in class, or 1/10 like we did today, okay? Can be absolutely anything. Now, if R is something like 2, then I'm gonna have times 2 squared times 2 to the 10th. That's gonna keep getting bigger and bigger and bigger. And although that might have lots of applications in terms of finite math, if we try to let it go to infinity, it's just gonna blow up. Okay, so can you see that there's special kinds of R's we want if we want to venture to infinity here? Can anybody guess infinity? There we go. What kinds of R's we might be looking for here? R equals 2 would be a bad idea if we're trying to go to infinity, because that's just going to grow and grow and grow and grow and grow. Yeah, if it's 1 over something like 1/10, 1/2, that's cool. Could we get away with something like, could R be, so let's see, R could be 1/2. We worked on that one the other day. Today we just did R equals 1/10. That worked out well. Could R be something like 4/5? Would that work out all right? So let's think about that for a moment. Let's consider just the sequence aside from the series. If I take 4/5 and I raise it to some power, like 3, that means take 4/5 times 4/5 times 4/5. Now 4/5 is less than 1, correct? So that means if I multiply by something by 4/5, it's going to be smaller than it used to be. So my point is that 4/5 to the power n is decreasing. Oops. Is decreasing. To double check that it's decreasing, I can use that formula we used the other day. Something is decreasing if the next term in line is smaller than it. So to double check the decreasing, I would say, okay, well, how does 4/5 to the n compare to 4/5 to the n plus 1? Well, 4/5 to the n plus 1 is just 4/5, oops, to the n times 4/5. I could divide out the 4/5 to the n, which is going to leave behind 1 is greater than 4/5, which on most good days is true, regardless of n. So we've just proved, yeah, it's always decreasing. Okay, always decreasing. It's also always positive, right? So 4/5 to the n is greater than 0. So it's always decreasing and greater than 0. What do we think the limit is going to be? Yeah, it's going to be 0. Now, just having a limit of the terms being 0 isn't good enough to show the sum is going to converge. And I'll show an example of that in a minute. So all this does here is this makes me hopeful about the series. But just because the individual terms I'm adding are getting smaller doesn't mean I'm necessarily going to have a sum that's going to converge. I don't know that. And this is important. We'll get to that more in a minute. So let's just take a look at our trick here. Suppose I look at the sequence, or the sum, excuse me, as I goes from 1, oh no, let's go from 0 to n of 4/5 to the I. That means I'm going to have 1 plus 4/5 plus 4/5 squared all the way up to 4/5 to the n. That's a partial sum. What I'm hoping is I can take the limit as n gets bigger and bigger and bigger and see where this is going. Now we could certainly add some up and take a look. So I could ask Desmos for some help with that. Remember in MyOpenMath in section 1, I put a link to this Desmos tool you guys can play with that helps me plot series and sequences. Probably should put another link somewhere else. Let's steal that link and just stick it right in the top here somewhere. Add a link. Desmos sequence grapher. I don't need any text there, and it is a web link. Bang. Open a new window. Show always. Create. Okay, so now if you just click that link right there at the top of section 10, it'll take you into this right here. So here I was graphing, what, 2 over n from the other day. I'm going to instead look at a sum. So let's see. I think I just type sum. Oh, and then it does that lovely thing. Now with the way I have this set up, it's putting an n here, but I also have an n there. It's going to get confused. So I got to say, you better not use n. That's going to mess things up. Let's use I or k, whatever makes you happy. Some letter I'm not already using. I wanted to start at 0, and I'm going to go up to, let's see, how do I make this work here? I think I want to use that n right there, n. And my formula here is 4/5 raised to the k then. All right, so this says if I add up 66 of those terms, I'm going to get 4.99999. Ooh, I wonder if it might be 5. So I could say, hey, give me 100 terms. Oh, it looks like, okay, so Desmos is saying, hey, yeah, do something, come up with a limit. Okay, so is this proof that it's 5? No, it's numerical evidence, but it's not proof. What we're about to do is prove it's going to be 5. So we're going to use that same trick we did a minute ago. The trick I used before was I multiplied by 1/10. Why 1/10? Because that was the base for my geometric series. So multiplying by the base, then I'm going to take 4/5 of s sub n, which is going to give me, it's just going to shift everything to the right. So it's going to give me a 4/5 instead of a 1, and then a 4/5 squared, and it's going to end at 4/5 to the n plus 1. Right? I bumped everything up 1 power by multiplying. If I do a subtraction then, uh-oh, this thing must be sliding. I'll switch over to here. If I do a subtraction, I'm subtracting everything. So on the left side, I'm going to have an s sub n minus 4/5 of s sub n. We'll clean that up in a sec. On the other side, let's see, there's nothing to match the 1, but those guys will subtract out. These guys will subtract out. Right before the n plus 1 will be a 4/5 to the n. So those guys will subtract out. So all that's left is the first term here and the last term there. So I'll have a 1 minus, right? Don't forget we're subtracting, 4/5 to the n plus 1. So exact same procedure as before, just different base. I could factor out the s sub n, which would leave me a 1 minus 4/5 on that, what's that, my left side? And that could be more simply written as what, 5 minus 4 is 1/5, right? So I'm going to have 1/5 of s sub n on this side, which I could just multiply over to the other side. So I think s sub n is equal to 5 times 1 minus 4/5 to the n plus 1. So now I have a shortcut. So if somebody says, hey, I need 100 of these guys, well, I can say, yeah, sure, no problem. The 100th partial sum is going to be 5 times parentheses 1 minus 4/5 to the power 101. I can whip that out of my calculator. According to Desmos, it's 4.9999999 something, because it calculated that for us. But I can do it without having to add up all 100 terms in between. Actually, there's 101 terms, right? Because we have that one in the beginning. But now we're at a stage where we can take the limit of the partial sums. So new page, I can say, hey, what's the limit as n gets big of these partial sums? Well, that would be the limit as n gets big of, what do we have, 5 times 1 minus 4/5 to the n plus 1. And we established earlier that as n gets big, this fraction to the power goes to 0. And so, hey, the limit is 5. So yeah, if you add enough terms here, it will add up to 5. Now, can you add infinitely many things? The answer is no, you can't. This is the limit of that process. You can get as close to 5 as you ever want. So if Clint said, hey, I need you to be within a gazillionth of 5, I can say, all right, add this many terms, that'll get you there. Okay. Remember we played around with that error calculation the other day when Melissa dared me to get close to that other sum. Same idea works here. In general, it doesn't really matter. I can apply this to any geometric series. So if we go to that general form of a geometric series, we're just going to reapply this trick one more time. So a geometric series partial sum is the sum as I goes from 0 to n of a times r to the I. And again, what that looks like is a plus ar plus ar squared all the way up to ar to the n. So what was our trick? Our trick was to multiply by r, okay, the base of my geometric thing. So I'm going to say, all right, what does r s sub n look like? Well, that kind of just shifts everything. That would be an ar plus an ar squared. There'll be an ar to the n, but we'll have an extra one at the n, an ar to the n plus 1 at the n. And then the next trick we applied here was we subtracted these two. So we'll get a s sub n minus r s sub n on that side. On the other side, it collapses, right? These guys subtract out, and those guys subtract out, and those guys subtract out. So on the other side, all I'm left with is the first term, a, minus this extra last term. Remember, I'm subtracting everything here. So I'll have a minus a r to the n plus 1. On the left side, I can factor out the s sub n kind of like I did before. So I'll have s sub n times 1 minus r. And I'm going to divide that over to the other side in a sec. So it looks like the partial sum, if you want 100 of them or 1,000 or maybe only 10, is always going to be the first term minus an extra last term, right? One more place out than we were originally heading, all divided by 1 minus your common base, r. Now this works for any r. R could be 2 and this would still work. R could be 1.5 and this would still work. I'm looking for things that go on forever. So if R is 2, I have a problem because 2 to the n grows without bound. Okay, so if we want to have the limit of partial sums turn into the real sum, that's going to give us the limit as n increases forever of a minus ar to the n plus 1 over 1 minus r. And we could factor that a out. I'm just going to leave it there for now. This is only going to converge if what? converges if, what can I say about R? It's got to be in between 0 and 1, yeah. So as long as R is bigger than 0, if it's 0, it's kind of lame, because then we just have, like, we have A, which is not much of a series. If R is 1, it's kind of lame too, because then what you would have, if we go back here, is A plus A plus A plus A plus A, kind of boring too. That would diverge. So R has to be definitely less than 1. It's got to be a proper fraction for this to work. So as long as that's true, I can take this limit. Well, if I take the limit, the only thing with an n in it is this guy here. And if I have R in this boundary, then I know that the limit as n gets big of R to the n, or R to the n plus 1 for that matter, that's going to be equal to 0. Okay, so what's left up here? Well, this whole thing just becomes 0 in the limit. So that means the limit of my geometric series, provided I have the right kind of R, is going to be the first term divided by 1 minus the common base. Well, that's kind of cool. That's quite sweet, short, beautiful. Now, I mentioned earlier that having your, this guy right here is basically the sequence, the individual term that we're adding, okay? Because I can factor out that A. So basically I have powers of R. In this case, if the powers of R go to 0, I have convergence. But just because your terms go to 0 isn't necessarily enough. So for example, let's take a look at what's called the harmonic series. The harmonic series is when we try to add up fractions. So let's let I go from 1 to n of 1 over I. So that would be 1 plus 1/2 plus 1/3 plus 1/4, on and on and on, up to 1 over n. So this is a partial sum, so I could say, hey, this is an S sub n. And then I could wonder, what about S, the limit of these guys as we let, we take, let n go out to 100, 1,000, a billion, a gazillion. So as n, my upper bound here goes to infinity of this thing. What is this thing doing? Well, we could ask Desmos, experiment with it a little bit and see. Where's Desmos? Right over here. Okay, so let's switch this to just, since I have 1 over k, starting at 0 would be a bad idea. So I'm going to start at 1, and then I have 1 over k. All right, so if I add 100 of them, I get 5. If I only added 50 of them, I get 4.5-ish. I could say, hey, let's add some more. Let's do 1,000 of these terms. So I could say, let's add a whole bunch. Let's see if I get up to 500-ish. What are we at? 6.8. If I go to 1,000, I'm up to 7. This thing is growing. I could plot these partial sums as points. To do that, I would start a point. I would say the x value for my point is one of these in the, let's see. I think I have to say it's one of these n values here. Let's double check. We'll find out in a sec. And then my y value is the partial sum. No, that's not going to work. I think I put a little n there, comma, and then sum as k goes from 1 to n of 1 over k. Will this do points for me? Ooh, what's that mean? Is that an error or is that a good thing? I don't see anything on the screen, so I must not have typed it right. Let's see, I did it before. What did I say? Oh, I got to use big N to make it happen. Okay. Where was I? Here? Okay, so that's got to be a big N. So the difference is N is just a counter, go that far. Big N is a list of all the numbers from 1 up to whatever that counter is. And GeoGebra, not, what is this one? Desmos, sorry. Desmos needs this list of numbers to make a bunch of points. So I just need to make that an N and this guy a big N. Ah, there we go. All right, so here is that sucker. And what did we had a lot of terms there. All right, does it look asymptotic? Doesn't look like it's, I mean, it looks like it's growing slow, but it doesn't seem to be settling down. It kind of reminds me of what? What functions have you seen that look like this? Square root function looks kind of like this, right? That grows forever. Natural log grows like this. That grows forever. So I don't know. Okay, so what do we have on our side? Well, we have on our side right now is that if we ignore the sum for a minute and we just focus on that last number, the limit as n goes to infinity of 1 over n, well, that's 0. Okay, that's a good start, but not enough. Good start. Maybe I have convergence, but I don't really know. So we're going to put a little trick here. I'm going to list out some more of these terms. We've got one, let's see, then 1/2 and 1/3. Oops, wrong place. 1/3, 1/4, 1/5, 1/6, 1, oops, wrong place again, 1/7, 1/8, and they just keep going and going and going. I'm going to group these things. I'm going to put those two together, and I'm going to put those two together. And then I'm going to say, like, what if I rewrote this, compare it to a different sequence? Come on, where are my tools? So I'm calling this sequence S, or this series S. I'm going to make a new series that I'm going to call, how about we call it X? And X is going to be a 1 plus a 1/2. Instead of that third right there, I'm gonna say, hey, let's call it a fourth instead. And this 5th, 6th, and 7th, I'm gonna say, let's call those all 1/8. That makes my life way easier. Okay. Now when I do that, these two 1/4, what do they add up to? It's a half. And these 4 1/8, what do they add up to? 1/2. Guess what I'm gonna do next, like out here? I'm gonna go 1/9 through 1/16. So that next group, 1/9 up to 1/16, I'm going to say, hey, let's all let those guys be 1/16. So then when I group those together, I'm going to have, let's see, 16 minus 8 is, there's 8 of those. I'm going to have 8/16, which is another half. So I'm just reorganizing the terms, and I'm let's see, what if this sum, is it bigger or smaller than the sum I'm trying to find? Which is bigger, S or X here? S is bigger. Okay, so what I know is that my new series I'm making, X, is always less than S. Okay, well, I'm adding a whole bunch of halves forever and ever and ever. What do you think that's going to add up to? If I added 100 halves, I'd have 50. 1,000 halves would be 500. A million halves would be 500,000. A gazillion halves would be half of a gazillion. So what's happening to X as N increases? What's that? It's always increasing, yeah. It's just half, however many terms I have, plus 1. I'm ignoring that plus 1 out there. So x is going to infinity also. So as n goes to infinity, x is going to infinity too. But wait a minute, s is bigger than x. So what must s be doing? It's going to infinity too. Yeah, it's not going all that fast, but it's going. Yeah, it's going. So my point here is that just knowing that the individual pieces are heading to 0 isn't enough. Isn't enough. You need more than that to say the sequence is going to converge. So this is just a super thing to be careful about. I can reverse it though. I can say if the pieces I'm adding, we usually call those the A sub n's. If these guys don't go to 0 in the limit, let's see, how do I write that? So do a few things. So if the limit as n increases of the things we're adding up, those are the terms, if that right there is not 0, I'm going to have a problem. If it's not 0, maybe it's 1, maybe it's a half. What happens if we add up infinitely many 1/2s? We have a problem, right? That doesn't work so good. So if this has any limiting value but 0, I have trouble. Then I can say the sum of those ANs as n goes from whatever to infinity, that diverges. So if the individual pieces aren't heading to 0, I know it diverges. This theorem has a very special name. I think you'll remember it. It's called the Divergence Theorem. So example, if I take the sum as n goes from 1 to infinity of 1.0001 to the power n, well, ignore the sum for a minute and just consider what those individual pieces are doing. 1.000, I have enough, to the n. Well, this number is bigger than 1, right? If you multiply by another number by something bigger than 1, isn't it bigger than what you started with? Yeah. So these guys right here are increasing. Right? The limit as n goes to infinity of these guys is infinite, which is not 0. So these guys are going to grow too. So this is going to diverge. You can't reverse this though. Just because the individual pieces you're adding shrink to 0 isn't good enough to get convergence. Okay, so the divergence theorem only does one thing. It just tells you if things diverge. It doesn't tell you anything about convergence. So if you have some sequence, or yeah, some sequence like a sub n equals, how about 1 over 2n minus 1. And then you try to add up those terms. I'm going to replace it with an I, actually. Just because the limit of the pieces goes to 0, I know nothing. This gives me no information. This is no useful information about the series. Okay. The only useful information I can get by taking the limit of the terms is if it's not 0. Then I can say, it doesn't go to 0. There's no way the sum can converge. There's no way the sum can converge. Okay. We're out of time for fun. So the material we went over today is in section 10.2 and 10.3. We covered quite a bit of stuff today. There's one topic I didn't get to in 10.3, and that's called telescoping series. So we'll have to take a look at that next week. But telescoping series aren't too bad. There's a good example in the book of that. And your homework is mostly for 10. For 10.2, it's mostly getting used to summation notation, which we're kind of already used to from Calc 2. In 10.3, it's playing with geometric series and the divergence theorem. When can you use this limit for positive purposes, and when does it like give you no information? Okay, and having an answer of 0 means I know nothing. Find some other reason. If it's not 0, then we're like, yes, it doesn't converge. And remember, there's multiple ways something cannot converge. It could bounce around for a while, never settle down, or it could just blow up, like go to infinity, or maybe negative infinity if it goes the other way. All right, that's it for now. Have